This is section 7.05 of the Unit 5 Notes, Math and Music. Today I am, as in you are the student, identifying transformations in music so that I can calculate frequencies of musical notes. I will know I have it when I can solve problems involving musical transformations. Specific TEKs we're looking at for today's lesson is 7a, use trigonometric ratios and functions available through technology to model periodic behavior in art and music. And 7c, use geometric transformations, proportions, and periodic motion to describe mathematical patterns and structure in music. Now, just to preface this lesson before we started, I am not an expert in music, so I'll do the best that I can to talk about these topics within the context of math and in this lesson. So you've been warned. First thing we're going to look at are transformations. So we've done transformations before in a couple of other lessons. This is just a review over the types of transformations we've used to describe certain things with shapes, how they go from one orientation to the other. So 4 of these transformations are translation, where we move the image from one side to the other without turning it or anything. Rotation, where we take the orientation of it and turn it around a central point with a certain radius around it. So as you can see here, the point is right on the tips of the arrow. And for this other image, you see the point is a distance away from it. And as it turns, it keeps the same radius all the way throughout to turn it around into a different spot. Reflection takes the image and mirrors it from one side to the other. So it'll be the same size, same shape. However, the orientation of it will be different. It'll be the left corner is going to be going to the right corner. The inside corner is still somewhat the inside corner. And then the top corner gets reflected to the top as well. So still keeping the same shape, same size, but oriented in a different way, reflecting it across a line. Glide reflection, where it takes the image, moves it, and then flips it across a reflection line. So it combines translation and reflection to create a glide reflection. Translates it and then reflects it across a line. To better illustrate this, I do have some GIFs to go along with those images. And again, translation, rotation, reflection, and glide reflection. You can just take a minute or take a few seconds to watch how those images animate and better understand what I mean when I say these terms here. Now, after we've gone over the transformations, again, we've done that particular part of that lesson before in previous lessons. So we're just going to go straight away into some practice to kind of remind ourselves of what is what. I want y'all, if y'all are on Class Kick 2, take each of these words here and match them to the correct image. We have rotation, reflection, and translation. So if you're on Class Kick, please move each of these words to the correct spot. And then if you want to check yourself, remove these boxes to see if you're correct or not. Yeah, so at this moment, go ahead and pause the video. Try this problem on your own. Otherwise, I'm just going to go straight into showing you what the answers are. So with the first image, it's a reflection. We can see a line in the left image and the right image mirroring each other. Notice how each of these have just kind of flipped over to the other side. If you want an example of that, hold your hands in prayer. Take one side, one hand, flip it out, and then take the other hand and flip that out. That is a reflection across the line that's between my pinkies. They mirror each other. So that's what a reflection is. Second one right in the middle is a rotation. As you can see on a axis that's away from these images, it has a central point of rotation with the same radius all the way throughout. Keeps the same size, same shape, but just orients it in a different location, making some of the ends point in a different way. And the last one is translation, where it just takes an image and then moves it to a different location. And that's it. These are the 3 or these are 3 of the 4 transformations that we talked about in the previous ones. That's it for We Try number 1. Now, again, I'm not the best music teacher. I'm not very learned on the topic, so I'm going to do my best to kind of point things out. Musical transformations. Many of the techniques used in writing music can be described using transformations. Music often contains transformations of notes in measures. So these right here, where the bar line is, before that bar line, this is a measure, and then the next part is the measure. This is a 4/4 time signature. So what that means is, for a 4/4 time signature, each measure gets 4 beats, 1, 2, 3, 4, and each beat gets a quarter measure to represent it. 1, 2, 3, 4. So in here, again, music often contains transformations of notes in measures. Here's a measure with notes, 4/4 time signature, 1, 2, 3, 4. And then we have a bar line to represent the next measure, 1, 2, 3, 4. Continuing on, for example, some songs have notes that repeat themselves. 3 blind mice. 3 blind mice. Notice how this first measure just repeats onto the second measure. So we can describe that as a transformation, translating it from one measure to the other. So it just moves from the left to the right, or vice versa. Usually we would describe that as left to right. Just going on with the next slide, so reading off of what it says. What happens next is very common in music. Those 3 notes are repeated. This is like translation in geometry. A repetition of notes can be an example of a translation. You also might hear other transformations, such as reflections and glide reflections. You can look at a line of music and determine if there is a transformation. So if you want, y'all can go ahead and zoom into this and see if you can find any transformations. So for example, I can see from here this third measure, or it looks like it could be about 5 measures in. This is a transformation. This can be transformed into the next one of the next measures down here. And then you could probably find other or translations down here. You could probably find other translations going on. You could find some reflections going on too. But if you want to take a look and try that yourself, be my guest. Going off of what we learned from our transformations, here are some examples of transformations in music. A translation, where we take one measure and just slide it over to make the next. A reflection, where the left side looks like the right side. We just flip it over an axis, the vertical axis right here. So this 4th note becomes the first note. This 3rd note becomes, or this 2nd note, because this is measured twice. This 2nd note becomes the 2nd over here, and the 1st note becomes the last note. And notice how they're all still on the same lines when we reflect it. A glide reflection, where we take one of the notes, move them across, and then flip them across the line. Notice how the line here is kind of flipped over. That doesn't really matter. What matters is the note is being reflected. Glide reflected, I should say. Same thing with these other 2. They glide over and then reflect across that line downwards. And then a translation and reflection. Notice how we have 3 measures here. So we're going to translate this first measure onto the second measure. Then we're going to take the second measure and then reflect it across the line here to make the third measure and reflect it. So these are all examples of transformations from what we've learned earlier in the video. Okay, so now I'm going to go through a series of polls that we would normally do in class, but because I'm doing this as a video, I'm just going to ask y'all to think about what's going on. I'm going to give y'all about I'll give you some time. You can go ahead and pause the video and take more time if you want, but look at this these 2 measures right here. These bars of music. What kind of geometric transformation is shown in this line of music? Do you see a reflection, translation, glide reflection, or rotation? So go ahead and pause the video, think about it for a little bit, and then unpause it and check your answer. And if you need a reference, there's a reference over here on the right, or you can scroll up if you're using the class kick notes up here to see which one is which. All right, and your answer should be a reflection. So it reflects from this bar line right here, from the left side to the right. Notice how this first note, this eighth note, gets reflected to the last position, the last note. This last note becomes the first note, and so on and so forth. So reflection is what happens here. Make sure I didn't skip any polls here. So the next poll: what kind of geometric transformation is shown below in this line of music? So again, check out your terms. Look at the examples right here. Determine which one you think best fits it: reflection, glide reflection, translation, or rotation. If you need more time, go ahead and pause the video, think about it, and then unpause the video when you think you are ready. Okay, so the answer for this problem, for we try poll number 3 poll, is glide reflection. So notice how this first note will, and it's a little bit midway through one of these, because notice where it is on the line. We glide it and then reflect it across the line right here. And then we take this one and reflect it down. This one reflected down. This one reflected down. Okay? So these are all glide reflected across from this line right here. Next poll: what kind of geometric transformation is shown in this line of music? Pause the video, think about it for a bit, and then unpause it when you're ready to check your answer. Okay, so for this problem, we have a translation. Now, I probably should have better shown it right here, but there is a translation going from here up. Let me use a different color there. So this note right here moves up one line, and again from here, up one line, and then up one line. Here were the original points of the notes, and they all moved up once. So there's a translation. There's no reflection going on, especially because you can't reflect this up here or this through a common line. They can only be translated up. Okay, so let's try this last one. What kind of geometric transformation is shown in this line of music? Think about it for a few seconds, then pause the video, think about it for a few seconds, and then after you're ready, go ahead and unpause it and check your answer here. Okay, with this, we have a glide reflection as well. This is probably not the best representation, but what does end up happening is these move. These do move in a certain way, either down or up. They're probably down to the next line right here, and then they reflect up to get to that top right here. And then here we do have another reflection as well. This moves just to where the next part is and then reflects upward as well. So there is a glide reflection going on where these two get moved down a line and then they reflect upward to the top right here. Same thing with this. This one, however, doesn't move up or down. It just reflects above. But overall, there is a glide reflection going on. Musical notes are actually just vibrations with a certain frequency. So the lower the note is, the lower the frequency, the higher the note on these lines, on these bars, the higher the frequency is. When you hear a musical note and then a different musical note, you are hearing a sound in one frequency and then a sound in a different frequency. If you're on Classic, I do have a virtual piano for you to try. And then a YouTube video that kind of explains frequency and musical notes. So if you have Classic open, you could play with that piano. I will click on the link and just kind of show y'all the website right here. Y'all could type that in and then try it out yourself. Every musical note has its own vibration called a frequency, which is measured in hertz. Higher frequencies correspond to higher notes, while lower frequencies correspond to lower notes. And then here we have a list of notes. B4, A4, G4, F4. Notice the numbers for them. B4 starting on a higher frequency, and then as we go down, lower in frequency. And then we get to the next set of frequencies, B3 to C3. B3 starts at 246 and then goes all the way down to 134 C3. Specific mathematical ratios can be used to determine frequencies of notes that are in harmony with each other. Every time you go up an octave, you double the frequency. So if we want to go up an octave, we want to double whatever the current frequency is. So A4 is equal to 2 times whatever A3 is. A3 on our chart is about 246.94 hertz. So, no, sorry, I got that one wrong. A3 is 220 hertz. And let's say we want to go up an octave to A4. So we're going to take whatever A3 is and then multiply it by 2. So 220 times 2 is 440 hertz, which you can see right up here. So just to show you an example of what's going on here, I don't know which hertz these are in, but I'm just going to play 2 A notes here. So I'm going to play a lower A note, then I'm going to play a higher A note, and then I'm going to play them together. Notice how they sound virtually the same. They're just, one of them is a higher octave than the other. And you can tell that those are different, the one lower. And then when I go on the A, it sounds virtually the same. Alright, so that was example number 6. Continuing up. If you ever want to go above an octave, for example, with C4 to C5, we know that the C4, the octave for that, the hertz for that is right here. So let me erase this. 261.63 hertz. And notice how C5 is not a part of our list of notes on the table. So we can't just simply look at the chart right here. If we want to get to C5, we need to double whatever C4 is. So we're going to take 261.63, multiply it by 2, and we will get 523.25 hertz to get the next octave up. Octave is like a range of sounds for your typical sounds, your set of sounds. Going up one octave goes up to a higher frequency to the same set of sounds, but in a different octave category. So Anyways, that's it. Now, I got you try number 6. If y'all are on Class Kick, I would like for y'all to go ahead and pause the video, read through the problem, and try it on your own. See if you can figure it out. And if, again, you're on Class Kick, you move this box to check your answers and see if you did everything right. Otherwise, I'm going to continue on and show y'all how to do this. The frequency of musical note D3 is 146.83 hertz. What is the frequency of D4, which is 1 octave above D3? Now, above means we're going to multiply. Okay, multiply to get to the octave above it. So D3 I know is 146.83. I'm just going to multiply that value by 2. $146.83 multiplied by 2, and I have 293.66. So 293.66, and there's my answer. And just to show y'all, that's exactly what we did. That's it for you try number 6. Okay, so now let's say, what is the frequency of F5, which is 2 octaves above F3? So it's very similar to what we did before, except now we want to do this twice. You can create a shortcut to go straight to the second octave, which is just multiplying by 4. However, we're going to do this step by step in this U-try right here. So for F5, we're going to start at F3. F3 is a certain frequency on the table. Y'all can figure that out on your own. You're going to multiply that by 2 to get F4. Then whatever you get for F4, you're going to multiply that by 2 again to get your final answer, F5. So go through this problem on your own. Pause the video, see if you can figure it out. Move this box to see if... whoops. I already showed y'all the answer. Pretend y'all didn't see that. I was just fixing something right there. Move that box to check your answer to see if you did everything correctly. So again, pause the video, try this on your own. Otherwise, I'm going to show y'all what to do. Okay, so again, what is the frequency of F5, which is 2 octaves above F3? What is F3? F3 is 174.61. So I'm going to multiply that by 2. 174.61 times 2 is 349.22. Notice how it's a little bit different here. This is rounded. So these are all values that are rounded to better use them in our calculations. This is our answer that we've calculated for right now. 349.22. We're then going to multiply that again by 2 to get to F5. So times 2 again. 698.44 about is our answer for F5. And that's it. That's it for you try number 7. Okay, so now we're going to look at going down frequencies instead of going up, or going down octaves instead of going up. So before, going up octaves, we had to multiply our frequency by 2. But now since we're going in reverse, going down an octave, we're going to half it, divide by 2 instead. So let's say my frequency is A4 and I want to go all the way down to A3. Well, whatever A4 is, I'm going to divide it by 2. A4 in this case is 440. So I'm going to divide it by 2 and I'm going to get A3, which is 220. That's it. That's it for example 8. So going the other way, going down an octave, you're going to half the note divided by 2. So you try number 8. The frequency of the musical note D3 is 146.83 hertz. What is the frequency of D2, which is 1 octave below D3? Fill it out, figure it out on your own, and get your answer. Move the box if you're on ClassKick to check your answer and see if you did everything correctly. Otherwise, pause the video if you want to do that. Otherwise, I'm going to continue on and show y'all how to do this. So again, the frequency of the musical note D3 is 146.83 hertz. And then we want to go down an octave, which means we want to divide D3 by 2. So 146.83 divided by 2. 146.83 divided by 2. Rounded to 2 decimal places, this is going to be about 73.42. So 73.42 is the octave below D3, D2. That is the frequency for D2. That's it for you try number 8. Now we're going to practice with getting 2 octaves below instead of 2 octaves above. So just like with 2 octaves above, we multiply twice, 2 twice to get 2 octaves above. So we're going to divide by 2 twice to get 2 octaves below. Okay, so I've given y'all the frequency for F3, which is 174.61. I now want to know what the frequency of F1 is, which is 2 octaves below F3. You can take a shortcut here and divide by 4, but we're going to do this through doing this through ClassKick. We're going to do this 1 octave at a time. So the first octave, we're going to divide F3 by 2, and then the second octave, whatever answer you get from that, we're going to divide again by 2 to get F1. So go ahead and pause the video, try this problem on your own, move this box to check your answer once you're done, only after you've done and tried it. Otherwise, I'm going to continue on and show y'all how to do this. Musical note F3 is 174.61 hertz. So F3 is 174.61. I want to get to F1. So first I need to get to F2. I need to divide this value by 2. 174.61 divided by 2. And I get 87.305. I'm not going to round here. 87.305, just so I can get more accurate numbers. I'm going to divide again to get to F1. So now F2 is 87.305. I'm going to divide by 2 again to get to F1. So now divide by 2. I have 43.65. So 43.65 is my frequency for F1 coming down from F3. And there we go. It's final answer for you try number 9. So there are other frequencies that sound good together, not just the same frequency up and below an octave. So there's something called a perfect fifth, which is the ratio 3 to 2. That ratio 3 to 2 is a frequency that sounds a particular way to us. So the way we calculate the perfect fifth above or below is through a proportion. So you'll see what I mean in a bit. So let's say we want to calculate the perfect fifth below. So the perfect fifth below is using this formula for 3/3, which is a fifth below, perfect fifth below. The frequency of the note above, and then the perfect fifth below note. So these notes will equal to 3/2, perfect fifth. Okay, so now we have a frequency of C4, and we want to get a perfect fifth below it. So the frequency of the note is going to go above C4, which if we go back to over here, C4 is 261.63. So we're going to use 261.63 at above, and we want to get the below part. We're going to cross multiply to find our answer here, because essentially what the bottom becomes is an unknown variable, x. So we need to solve for x through proportions, cross multiplying those proportions. So now 3 times x is 3x. 2 times 261.63 turns into 523.26. We're then going to divide both sides by 3, getting the x by itself, rounding our answer, we get 174.42, which is about F3, 174.42. So it's F3 is our perfect fifth below C4. Again, I don't have the frequencies on here, but I'm going to show you an example of what a perfect fifth looks like, or at least sounds like. So here's C, and then here is F, which is the frequency below C4. So again, this is a perfect fifth before. F4 would be right here, theoretically, and then F3 is below it. Now when I play them individually, you can hear them. And then when I play them together, they have a certain sound that sounds like they go together. So that's what a perfect fifth does. That's what a perfect fifth does. It pairs two sounds that sound good together. And this is all mathematically done to find it. It's not, you can just kind of play around and see what sounds good, but mathematically, these two notes go together. All right, you try number 10. What is the frequency of the note that is a perfect fifth below G3? Look for G3. Figure out, well, I've kind of set it up right there where it's supposed to go. Perfect fifth below means the G3 value is going to go above, and we're trying to find the below, which turns into X. So go through the work, cross multiply and divide, and then get your final answer. See if you can figure it out on your own. Move the box to check your work. And yeah. So, go ahead and pause the video, try this on your own. Otherwise, I'm going to go ahead and show y'all how to do this. So, G3 is 196. I'm going to cross multiply to get my perfect fifth below G3. So, x times 3 is 3x. 196 times 2 will turn into 392. And then I'm going to take 392 and divide it by 3. I'm going to divide both sides by 3. X should be by itself now. 392 divided by 3 is 130.67. So 130.67, which means C3 is our perfect fifth below G3. And just to show y'all how that sounds on this virtual piano, I'm going to pick G, G3, and then C3. I'm going to play them together. Let me choose a higher frequency, G3, or let's pretend again this is G, and then C. And I'm going to play these again. So you can see how they kind of resonate with each other. Even though they're different notes, they have a frequency that sounds pleasant together. A perfect fifth below. Okay, so now we're going to go through an example of a perfect fifth above the notes. Okay, just grabbing this formula here to show y'all. So notice how we're still using the same ratio. However, the note that we want is going to be above the fraction bar. So the perfect fifth above C4 is the part that's going to turn into the X. And then the C4 ends up being at the bottom of our proportion. So 261.63. C4 will then, or both fractions will get cross multiplied. So now this is 3 times 261.63, which equals 784.89. 2 times X turns into 2X. Next thing I'm going to do is divide it by 2. And running it through the calculator, I get 392.45. 392.45 is G. So the perfect fifth above G is C. And we already kind of did it before in a previous example. We found out that G3, perfect fifth below, is C3. Well, the perfect fifth above G3 is C4 as well. So here's G. C3 is down here. And then C above it is also the same. So again, you can kind of tell with your ears how they sound and how pleasant they sound. That's it for that example. Example number 11. Now there's a U-try. U-try number 11, the last U-try of this lesson. We have a frequency of the musical note B4, which is 493.88 hertz. What is the frequency of the note? That is a perfect fifth above B4. So again, notice the formula, and since we want it above, this note has to be below the formula right here. And then the top part is going to turn into an X, cross multiply, divide, and get your answer. Move this box if you're on Class Kick to check your work, see if you're doing everything correctly. So at this moment, I would like for y'all to pause the video, try this on your own. Otherwise, I'm going to continue on and show y'all this last problem. So again, we're going to set up this proportion here. 3 over 2 is equal to X over 493.88. And it's at the bottom because we're looking at above. So above means this goes below. Cross multiply, X times 2 turns into 2X. 3 times 493.88. We'll multiply that real quick. 493.88 times 3 is 1481.64. Divide this by 2. Divide both sides by 2. And our final answer should be 740.82. And that is the perfect fifth above B4. 740.82. That's it for U-Try number 11. That's it for 7.05 notes and Unit 7 in general. So if y'all have any questions, make sure to answer your teacher. If I'm your teacher, make sure to ask me. If you need to go through any of these topics again, remember this is a video, so just rewind it over those problems and see if you can understand it by just repetition of the content over and over again. That's how math is. That's how working out your brain is, repeating the same things over and over again until it sticks. So that's it for this video. I'll see y'all next time. Take it easy, everybody.